In this video, we work example 3 for our unit 3, lesson 3, which is extreme extrema on a closed interval. So we've got this function. It involves a rational exponent, which I think makes it unique as compared to the other functions. H of x is equal to 3 times x to the 2/3 minus 2x plus 1. And we're only interested in the part of the graph on the interval from x equals -1 to x equals 2. First of all, the question says, does the extreme value theorem apply? And we know the answer is yes, because the extreme value theorem applies if two things are satisfied. The function itself has to be continuous. And this function is definitely continuous on its domain. Functions with rational exponents are continuous on their domains, Polynomial functions are continuous on their domains. So if you add them or subtract them, they're going to be continuous on their domains as well. This is continuous on its domain, and we're talking about a closed interval. So an interval from A to B, including the endpoints. In this case, A is -1 and B is 2. So both of those things are satisfied. We're on a closed interval and we have a continuous function, so the extreme value theorem applies. Now remember what the extreme value theorem says. It says that if the function is continuous and we're on a closed interval, then we're guaranteed to have an absolute max and an absolute min on that interval. And so we're saying, yes, it applies. Now we're asked to find the absolute extrema of that function on that interval. Well, the extrema can occur at a number of places. They can either occur at the critical values on the interval, or they can occur at the endpoints. So first, let's evaluate h at the endpoints, see what the function values are. So we've got h evaluated at x, which is given by this. I'm using these open parentheses to represent where I'd like to plug in the x values. Then I'm going to substitute in x equals -1. Now, remember this notation, it means take this number and square it and then take the cube root. So we're taking the cube root of -1 squared. -2 times -1 is +2. -1 squared is +1. You take the cube root of +1, you get 1. So this is 3 plus 2 plus 1, which is 6. And then at x equals 2, the y value on the graph is 3 times 2 to the 2/3 minus 2 times 2 plus 1. And 2 to the 2/3 can't really be simplified, so I'll just leave it alone. This is -4 plus 1, which is -3. And that is approximately equal to 1.762. I actually calculated that using a calculator. I think I used Desmos actually before the video started. So we know that when x equals -1, the y value on the graph is 6. And when x equals 2, the y value in the graph is 1.762 approximately. So we can graph that function. Even if we don't know the rest of what it looks like, we know that at -1, the y value is 6. I know that that's true. And I know that at x equals 2, the y value is approximately 1.762 or about 1.8-ish. And so we get that value. And we're still dealing with this function right here. The question says, okay, find the absolute extrema on the interval. Well, the way we find the absolute extrema on the interval is we're looking for absolute minimums and the absolute minimum value of the function on the interval and the absolute maximum value of the function on the interval, That's what extrema means. So we want the min and the max. We know the way we find the absolute min and the absolute max is we evaluate the function at the endpoints. We traditionally call this the interval from A to B. So then A equals -1 and B equals 2. And then we find the critical points of H on the interval of interest and evaluate H at the critical points. Now remember what the critical points are. Critical points of our function are the x values in the domain where the function's derivative is equal to 0 or the derivative does not exist. So again, we're looking for those points where the derivative is either 0 or does not exist on the interval of interest. So to do that, the first thing we do is compute h prime. So it's the derivative with respect to x of 3 times x to the 2/3 minus 2x plus 1. And we compute that derivative term by term. The derivative of 3 times the function is 3 times the derivative of the function. The derivative of an x to some power is that power times x to the 1 less power. 2/3 minus 1 is 2/3 minus 3/3, which is -1/3. The derivative of a constant times x is just a constant, and the derivative of a constant by itself is 0. So we get this. And so we've got 2 times x to the -1/3 minus 2 as our h prime. Now it helps to remember our exponent properties here. And that x to the -1/3 is actually a fraction. It's a little bit difficult to see, but x to a negative power is the same as 1 over x to the same power but positive. So this 2 is multiplying 1 divided by x to the same power but positive. And we're subtracting 2 from it. And this fraction we can write as, or this number we can write as itself over 1. So if we multiply straight across, we get 2 divided by x to the 1/3. And if you want to, in order to find those points where h prime equals 0, it's helpful to get a common denominator in this case, because we're going to have a fraction here. We probably want a fraction here so that we can combine them. And then we can set the numerator equal to 0. That's when the derivative will be equal to 0. So I want a common denominator where my denominator is this x to the 1/3. I want the least common denominator, x to the 1/3 and 1, which is just x to the 1/3. So I'll multiply this by x to the 1/3 divided by x to the 1/3, excuse me. That's called a well-chosen 1. It doesn't change the value of the fraction. It just changes the way that we're writing it, with the exception of saying that x can't be 0, because when I multiply by this quantity can't be 0 divided by 0. That would be that would be against the rules. That would not be allowed. So we've got this is equal to the -2, except for when x equals 0. And now we can combine these expressions. So I end up with 2 minus 2 times x to the 1/3, all divided by x to the 1/3 is my h prime of x. And I'm still looking for those x values that cause that h prime to be 0 or that cause the h prime to be undefined. Well, we know that we can't divide by 0, so h prime is undefined when x is equal to 0. Or in other words, we say h prime does not exist when x to the 1/3, that's the denominator, equals 0, which implies that x equals 0 is a critical point. And it's a critical point where the derivative is undefined. So we'll want to evaluate our function at that critical point. Sorry, it's getting a little bright in here. I don't know what's going on with my camera. And then h prime is equal to 0 when that fraction equals 0. So we had 2 minus 2 to be, or 2 minus 2 times x to the 1/3, all divided by x to the 1/3 equals 0. Provided that x doesn't equal 0, we can multiply both sides by that quantity, and we just get that the numerator equals 0. If you want, you could factor out the 2. And then divide both sides by 2. I don't know what's going on with this. Sometimes it's helpful if I put some other colors in the screen. I don't know what's going on. Here we go. In view, not in the screen, you know what I mean. So I have 2 equals 0, which is never true, or this equals 0, which means that 1 minus x to the 1/3 must be 0. So 1 has to be equal to x to the 1/3. To get rid of that cube root, we cube both sides, and x has to be equal to 1. So x equals 0 is a critical point, and x equals 1 is a critical point. And we are only interested in those critical points on the interval from -1 to 2. Well, 0 and 1 are both on the interval from -1 to 2. So we evaluate the function at the critical points. We have h of 0, and we want to compute h of 1 as well. And I don't remember what the function is. It was 3 times x to the 2/3. So it's 3 times my input to the 2/3 minus 2 times my input plus 1. I like this notation because it just sort of helps us to remember where we're substituting our x values. We substitute x equals 0, we get this. That's 0, and then we're adding 1. So we get 1 there. And at x equals 1, we've got 3 minus 2 plus 1, which is 4 minus 2, which is 2. So you've got these 4 y values. You had these two when x equals 0, h equals 1. And we know that when x equals 1, y equals 2. And we don't know any other details about the graph looks like. We know that it starts here, and then it goes here, and then it goes here, and then it goes here, as x goes from -1 to 0 to 1 and then to 2. The question is, does it have an absolute value, or excuse me, or what is the absolute maximum and what is the absolute minimum? Well, the absolute maximum is the largest y value in this list. Well, obviously the largest y value is 6. So this is going to be our absolute max. And the question is, what is the smallest y value on this list? Well, this is a y value of 1. This is a y value of 2. That's a y value of, what was it? Approximately 1.762. So the smallest y value is this one. And you might wonder, okay, well, what does the rest of the graph look like? How does the curve change as we get from this point to this point? Is it just a line, or does it curve one way or the other way, or does it do something interesting in between? You know, how do I get from here to here or here? Like, how does all of that happen? If we want to see that, we can always use a graphing calculator to get a better sense of our graph. Let's look at what our graph looks like. But I know that all we know at this point is just based on the form of this function. This is a function with a rational exponent. This is a polynomial function. This is the sum of the two of those. So we know it's continuous. We know that these points have to be connected to each other. We just don't know how. We don't know how the curve changes as we go from here to here. But we do know that it doesn't have a maximum or a minimum. There's not really much interesting that's happening, but like, does it curve sort of like this, or does it curve sort of like that? You know, is it a straight line? Like, what happens in between those points? We don't know unless we use a calculator, or in future sections we'll look at the second derivative as well as the first derivative, and we'll be able to infer more about what happens on the interior here. But a couple of things I want to point out. At this point and this point, we didn't even concern ourselves with what the slope was. But if we wanted to, we could substitute x equals -1 and x equals 2 into our derivative function and find the appropriate slope at those locations. We know that at x equals 0, that derivative is undefined. So I'm expecting some kind of sharp corner there. I'm expecting different derivatives from the left and the right, different behavior for the derivative function from the left and the right for x equals 0, because h prime is undefined at x equals 0. And I know that h prime is equal to 0 and x equals 1. So that means at this point, I'm expecting everything to be nice and smooth. And so if I'm starting down here and I'm ending up over here, I bet that's a relative max rather than just a flat point where we're increasing and then have a 0 slope and then increasing again, or decreasing and then have a 0 slope and decreasing again, because I know that these 4 points are on my curve. Let's verify that using Desmos.com. Okay, so this is our function, example 3. So we've got h sub 2 of x is equal to this. I just used 2 because I'm not interested in this particular function as it stands. I'm only interested in part of this function. I'm interested in the part between x equals -1 and x equals 2. So that's the graph that we're actually interested in. It starts at this location and ends at this location. If we evaluate the function at x equals -1 and x equals 2, we can find the corresponding y values. So those 2 blue points, and we can label them. Desmos.com has evaluated h of -1 for us, and they told us that the h value was 6, which is consistent with what we did on paper. And then when we substitute in x equals 2, We get this number, which is also consistent with what we got on paper, was 3 times 2 to the 2/3 power minus 3. Let me just check. 3 times 2 to the 2/3 power minus 3. Yep, same thing. Yep, so that's h of 2. So Desmos.com calculated those for us. And then we said, okay, the absolute extrema can occur either at the endpoints or on the interior of the interval. So in order to find the absolute extrema, we need to find those points. And then the highest y value is the absolute max, and the smallest y value is the absolute min. How do we find those y values? Well, to find the critical values, the first thing we do is compute the derivative. So we computed the derivative using the power rule and the derivative of a sum and the constant multiple rule is the combination of all of those rules. And eventually we got h prime equals this 2 times x to the negative 1/3 minus 2. And if we rewrite that as a fraction, because we've got the x to the negative power, x to the negative 1/3 power, we want to rewrite that first expression as a fraction. Then we've got one fraction minus a constant 2. We want to combine like terms so that we get the entire expression written as a single quotient. And then we said, okay, when is this function undefined? Well, it's undefined when h is equal to, or when x is equal to 0, because we end up with that x in the denominator. So we said, okay, well then if h prime is undefined when x equals 0, x equals 0 must be a critical point. So let's find the function value at the critical point. And it turns out that the function value is 1. We substitute an x equals 0 here, we get a 1 for our y value. And say, okay. And that's consistent with our image there. Our image shows us that the derivative is undefined at x equals 0. Looks like the slopes as we approach x from, or x equals 0 from the left are all negative. And as we approach x equals 0 from the right, the slopes are positive. So we would expect the derivative to be undefined there, and it is. And so that is a potential relative extremum. And we can tell just from looking at it that it's a relative min. It's the lowest y value in the area. All the other y values nearby are higher than it. So we've got that. And then you might say, okay, the other x value comes from setting the derivative equal to 0 and solving for x. We did a bunch of algebra. We wrote the h prime as a single quotient, and then we said, okay, the only way that quotient is 0 is if the numerator is 0 and the denominator is non-zero. And so we set the numerator to be equal to 0 when the denominator was non-zero, and we found a particular x value. You might say, how do I do that without having to do all that algebra? I'd rather not do the algebra. Well, you can just look at the tangent line and try to find the x value where that tangent line is horizontal. So this little slider is going to allow us to view the tangent line for various values of our x value on the interval from -1 to 1. So here's the point of interest. And then we're going to let that point move and then watch the tangent line change as we go from point to point. Now I'm trying to find a point where the slope is 0, and I've added this little cell right here, which actually computes the slope at that particular x value. I think the slope is 0 right here, and it looks like x equals 1 to me. So let's type in x equals 1 for b. And look, h prime of 1 is equals to 0. So yes, that is a critical point on the interval from -1 to 2. H prime of 1 equals 0, so x equals 1 is a critical point. That's also the same value that we found when we did all the work by hand. So the geometric interpretation using the computer is consistent with all of the handwritten work that we've done. So we've got that. Let's get rid of that tangent line right now. And we'll label that point. And I think we're ready to answer the question. We've evaluated the function at the endpoints. We've evaluated the function at the critical points on the interior of the interval. The question is, what is the relative minimum and what is the absolute minimum and what is the absolute max? Well, the smallest y value is obviously the one at the very bottom of the graph. Y is equal to 1 down here, so that's the absolute minimum. And the absolute maximum of our function on the interval is this x equals 6, or excuse me, y equals 6. And it occurs when x equals -1. So we get an absolute max of 1 when x equals 0. We get an absolute min of 1 when x equals 0, excuse me. And we get an absolute max of 6 when x equals -1. And then these other 2 points are actually relative extrema as well, but we couldn't really tell that without like actually viewing this graph. I think we could guess that that was implied by assuming that the function was continuous as we went from this point to this point to this point to this point. We would assume that this point 1, 2 corresponds to a relative max of 2 at a location x equals 1, and that this point x equals, or this point corresponds to a relative minimum of approximately 1.762 when x equals 2, because it's the smallest y value in the area. We could assume all of those things, but we don't actually know them doing all of our pencil and paper calculations. Like we could guess, and we're probably right, but we need a little bit more calculus to know how the graph behaves in between those 4 points of interest. So we're able to solve the problem. The question asked us, what are the absolute maximum and minimum value of the function? Let's write that down. The absolute max of h on the interval of interest, which is the interval from -1 to 2. Is 6, and it occurs at x equals -1, and the absolute min of h on the interval of interest is 1, and it occurs at x equals 0. And we can see from the graph that we have a relative max of 2 at 1, and we have a relative min of 1.762 at 2. But there's nothing from our handwritten work to justify that completely. But our handwritten work suggests that. We might say, how can I prove that? We're going to be able to prove that using the first derivative test and the second derivative test in a later section. But another way to analyze this is to just look at the derivative as a function. We've already computed that derivative. We computed it here. And if we look at it, we can see sort of the values of the slope for the points of interest. I actually think I want to get rid of some of these labels because they're sort of cluttering up our graph. So we can see that as we approach x equals 0, the slope function is, or this, this tail function is giving us the slope of the graph at that particular x value. So as our x value approaches 0, the slope is going to positive infinity as we approach from the right. And as we approach x equals 0 from the left, the slope is going to negative infinity. That's easier to see when we include that point. And we draw a tangent line there, and then we let this vary. See, there's my slope. As we approach 0 from the right, that slope is going to positive infinity. It almost looks like it's going to negative infinity because you're looking at it the wrong way. You're still looking at the slope of the line as it goes from left to right, and it's very large and positive. And as we get closer to b equals 0, that slope gets larger and larger. But then when we switch sides, when our b value is negative, when we're over here, all those slopes are negative, and they get increasingly negative, more and more negative as we approach x equals 0. And those values are accounted for on this teal graph as well. You might wonder, okay, well, what is that point? That's going to give us the slope when x is equal to -1. Well, I could just move this point up here at x equals -1. You might say, what is the slope? You could figure out that slope by adding some minor grid lines and then just using rise over run to calculate it. Or you can just plot the point h prime of -1 at -1, and the slope is given to be -4. So we start here, we go down 4, and we go over 1 to get another point on the line. Oh, it doesn't look right, does it? Oh, it does. Down 4 and over 1. There it is. To get another point on the line. So we know that that slope is -4 there. And then as we let b increase, our slope gets larger and larger. So you can take this point, you can do the rise over run thing, you can count the number of, what's it called? Squares that you go down. You can look at, how many squares is my y changing by as my x changes by a particular number of squares. This is allowing us to count like how far we're going in the y direction for every change in the x direction. Or you can just actually plot that point B and H prime. Let's label it. So at this location, when x is equal to negative 0.15, the corresponding slope is negative 5.764. So we go down 5.764 units in the x or in the y direction when we go 1 unit to the right in the x direction. So as our b increases, those slopes get larger and larger until we get to near 0. And then it flips. It goes from negative to positive. And then those slopes go from very large and positive to less positive to less positive to less positive until eventually they get to 0 at the top there when x or b equals 1. And then as you continue, as your b increases from 1 to 2, that slope becomes increasingly negative. But if you want to, you can evaluate the derivative at -1 and 2. You can find the derivative values at those locations. And you can compare those to the tangent line. Now our graph is a little bit busy. It's a little too busy for me. The y values on that teal graph are giving the slope of that tangent line at that particular location. Now, if we were bad at algebra, let's say we don't actually know how to find the x value where the derivative is 0. You always have the option, or in some courses, you have the option, depending on your teacher, of just looking at a graph of the derivative and figuring out where that derivative is equal to 0. I'm like, it looks like it's 0 right there. The derivative is 0 when x equals 1. And then if I look at the tangent line when x equals 1, I'm pretty sure that's going to be a horizontal tangent line. You can always check by substituting b equals 1 and then drawing the tangent line. Look, the derivative is 0 there. And say the derivative is 0 there, and the slope is 0 there, and the derivative value is 0. So this is right. I think it's consistent. So that's telling us that at a minimum, that point or that critical value x equals 1 corresponds to an x value where the original function has a 0 slope. Now that location might correspond to a relative minimum or a relative maximum, or it might just be a flat spot where the function goes from increasing to 0 to increasing, or increasing to 0 slope to increasing, or decreasing to 0 slope to decreasing. Either one of those would be fine. But there's nothing yet from our discussion that tells us that that's going to be a relative max rather than a relative min. But you might say, how can I figure that out? Well, let's get rid of that tangent line again. Look at what this derivative shows us. At x equals 1, our derivative function goes from positive to negative. So we go from a positive slope to a much smaller positive slope, and then we have a 0 slope, and then we go from to a negative slope, and that negative slope gets larger in magnitude until it reaches this point. That's consistent with this picture, because these slopes, if I look at the tangent lines over here, they're all going to have a positive slope. Or between 0 and 1, all of those have a positive slope. If we look at them from left to right, the y values increase. They go up as we go from left to right. And then when we get to x equals 1, we get 0. And then as we continue from x equals 1 to 2, the that's sloping the other way, so the slope is negative. Does that make sense? So we've got positive slope. And then at that location, we have a 0 slope, and then we have negative slope. Now think about that while looking at this teal curve. Positive slope that's getting less steep and less steep and less steep, and then we have a 0 slope, and then we have a slope that's getting increasingly steep and much more negative as we go to the right. So you can see that when our derivative goes from positive to 0 to negative, what we have is relative max. Visually, we can see that. That's a sort of a preview of what's called the first derivative test. It's a little bit unrelated to the extreme value theorem, but it is related to finding extrema. Okay, let's get rid of this line. And let's get rid of the derivative graph for now. And then let's look at this function. And say, okay, well, how do I do my homework? How do I answer questions about the extreme value theorem? It's actually very simple. Usually when you're asked about the extreme value theorem, you're given some function and you're told, yeah, here's your function. We're only interested in part of the function. We're interested in that part in this interval. It's always a good idea to find the corresponding y values for the end of the interval. So I like to plot those points and label them. And then you say to yourself, okay, does the extreme value theorem apply? And it does. This function is continuous because it's a sum of continuous functions. It's continuous. Are we on a closed interval? Yes. So we're guaranteed an absolute min and an absolute max. Where are the where are the locations for the absolute max and absolute min? Like, where are the possible locations for the absolute max and absolute min? They're on the exterior of the interval at the endpoints, or they might be on the interior at one of our critical points. So we evaluate the function at the endpoints. We find the y value of 6 and a y value of this approximately 1.762. And then we find the derivative, find critical points. We set the derivative equal to 0. We find that it's we find that it's equal to 0 when x equals 1 and undefined when x equals 0. And then we evaluate the function at those points. And then we just look at the y values and we say, which one's the largest y value? 6 is, that's our absolute max. Which one's the smallest y value? 1 is, that's our absolute min. And then there's other values we can't be sure about, but there's something called the first derivative test that will allow us to infer later that this point corresponds to a relative max. And then we can just look at the graph. We see that it's decreasing as we get to here. So this is the lowest y value in the area. That means that that point is a relative min on the particular. That's it for example 3. In the next few videos, we'll look at more interesting examples. Inverse trig functions, logarithmic functions, exponential functions. But we're pretty much doing the same thing with those functions as we've done with the last 3 functions. That's it for now. Let me know if you have any questions.